start with this lecture on strained layer epitaxy. In the last class, I discussed about lattice matched heterostructures, growth of lattice matched heterostructures. So, this is what we discussed in the last class, and I had mentioned that if there is a lattice mismatch, if the lattice constant of the substrate As, if As is the lattice constant of the substrate, and Al is the lattice constant of the layer that is being grown, of the layer, the epi layer, actually the layer being grown epitaxially, then we wanted that Al As must be equal to Al. So, this is lattice matching. But what would happen if As is not equal to Al? In the last class, in our discussion, I showed that if As is not equal to Al, there are some atoms which do not participate in the bonding, and then there are dangling bonds which are defects in the medium, and the defects always increase the possibility of non-radiative recombinations, which is detrimental to the performance of optoelectronic devices. Is it true that we cannot grow this at all if As is not equal to Al? If As is not equal to Al, even then we can grow defect free structures, provided there are certain conditions, provided the thickness of the layer is below a critical thickness. If the thickness of the layer that is being grown is less than a critical thickness, then it is possible to grow defect free structures, and this is called strained layer epitaxy. It is called strained layer epitaxy because in that case there will be built-in strain in the medium. So, let me illustrate this strained layer epitaxy. So, epitaxy is growing on top, epitaxis. So, if you start with a substrate, as before, let me show a one-dimensional structure, which means I have atoms sitting in a one-dimensional lattice. So, this is the top monolayer that I am showing. This is the substrate. Which is characterized by As. If I want to grow a layer on top of this, which has a larger, let us say I want to grow a monolayer of this, which has a slightly larger So, this layer has Al, the lattice constant here in one dimension, the separation between two atoms is Al, lattice constant. This is now not matching. In the last class, I had said that this will result in dangling bonds. And defects. However, if the thickness of the layer is very small, what is this very small we will quantify. If the thickness of the layer is very small, it is possible to form lattice matching. What would happen is the atoms in this layer, which is a very small thickness, adjust themselves, reduce their lattice constant, that is, there would be a built-in strain in this direction, a compressive strain from the sides, which will result in a compressive strain here will lead to an elongated strain or tensile stress strain in this direction, a compressive strain from the sides and a tensile strain in this direction. So, these atoms will feel a tensile strain in the vertical direction, compressive strain from here. To match these atoms, exactly to match this. So, what would happen is this would result in a structure I will show a smaller portion here. I am taking a square lattice just to illustrate the point. So, this is square, this was also square before they formed bond, but when they form, what happens is let me draw it and then it will become clear. This was the interface. Please see, this was the substrate. This is the interface. This gap, interface here. So, the interface is here. So, it had square lattice here, but what has happened in this direction is when it tried to adjust itself in this direction by experiencing a compressive strain, then it gets extended in this direction. It has become rectangle in this direction because the atoms have been pushed to accommodate the size here. So, at the interface we have AS equal to AL. Before this, so this was AL. So, AS not equal to AL, AS not equal to AL, but it has adjusted itself so that AS has become equal to AL in this direction at the interface. But there is a built-in strain now, and hence they are called strained layer epitaxy. It is a strained layer epitaxy because there is built-in strain on the layer that you have grown. Hence the name strained layer epitaxy. But there is a restriction. When can the atom adjust itself? When can the layer adjust itself? Provided the thickness of the layer that you are growing here, the thickness, if I call this as this thickness was d, if this is dl, then if this thickness dl, if dl is less than a critical thickness dc. So, dc is the critical thickness. Critical thickness. This critical thickness dc is given by an empirical relation approximately equal to As divided by twice mod epsilon, where epsilon is called the mismatch parameter. So, epsilon is equal to Al minus As divided by Al. Al minus As divided by Al is called the mismatch parameter or mismatch. It is a measure of mismatch. When epsilon equal to 0, that means AL equal to AS, it is perfectly lattice matched structure. But when epsilon is not 0, it means AL is not equal to AS, therefore, epsilon is the mismatch parameter. If the thickness of the layer, epitaxial layer which is being grown, if it is less than a critical thickness, then it is possible for the atoms in the layer lattice here to get adjusted, although there will be a built-in strain. In the resulting structure, there will be a built-in strain, but the layers can get adjusted. You can think of an example of a sheet of rubber sheet. Okay. If it is very thin, you can stretch it. Rubber you can stretch if it is thin. If I give you a thick block of rubber, you just can't stretch it. It is just like a solid, you just can't stretch it. But if the rubber sheet is thin, then it is possible to stretch it. It is exactly that what is happening, that if the thickness of this layer is very small, then it will adjust itself so that it matches this lattice. With the additional feature that there are compressive strains, built-in strains, and this is called strained layer epitaxy. There are no defects, no dangling bonds. It has adjusted itself, but in the process of adjustment there is built-in strain in the structure, hence the name strained layer epitaxy. Let us put some numbers into this and see what kind of thicknesses are acceptable, which will make it more clear. And then we will also quantify this parameter, which is the mismatch parameter. Let us say the substrate lattice constant AS is equal to 5 angstrom. As you know, typically most of the semiconductors have AS substrate lattice constant anywhere from 5.5 to 6 angstroms. So, let me take AS equal to 5 angstrom. If epsilon, generally people talk in terms of percentage, if epsilon is 1% to 10%, this is the kind of mismatch which is 10% means epsilon equal to 0.1, expressed in percentage is 10%. This ratio is 0.1, that is 10% mismatch. 1% means epsilon equal to 0.01. So, let us see what is DC, the critical thickness, equal to, if I put 1%, then AS is 5 angstrom divided by twice into epsilon is this much, that is 2 into 0.01, 1%. How much is this? 250 angstrom. The critical thickness is 250 angstrom. So, if a lattice mismatch of 1% can be tolerated provided the thickness of the layer is less than 250 angstrom. If you are growing only a thin layer with thickness less than 250 angstrom, then that lattice mismatch can be tolerated. If you put 10% mismatch, 10%, so DC will be equal to, so this is for 1%, because most of the times the mismatch is talked in terms of percentage, but remember that it means epsilon is this much. So, DC will be equal to for 10% mismatch, what do you expect the thickness of the layer to be? Much smaller, because mismatch is more, therefore, only it has to adjust more itself, therefore, a thinner layer would get adjusted. So, DC is equal to 5 angstrom divided by 2 into 0.1, which is 25 angstrom. So, if the layer that is being grown is less than 25 angstrom, then that material can stretch itself and get adjusted with a built-in strain. The numbers are very small, 250 angstrom, 10 angstrom, 25 angstroms. Are these practical? Do they have any practical significance? Yes. If you are talking of layers with the dl of the order of 100 angstrom, what are we talking of? We are thinking of quantum well structures. If the thickness is of the order of 100 angstrom, then we are talking of quantum well structures. Why are we talking of quantum well structures? What are quantum well structures? Quantum well structures are structures where the dimension of the layer, when the dimension of the layer is less than or of the order of the de Broglie wavelength of electrons in the medium. So, structures in which the dimension, that is dl, is less than or of the order of de Broglie wavelength are called quantum well structures. What is the de Broglie wavelength? De Broglie wavelength, did I calculate earlier? The de Broglie wavelength, lambda de Broglie, let me calculate de Broglie for a semiconductor, let us say in, for example, in gallium arsenide. I want to calculate lambda de Broglie of electrons in the semiconductor gallium arsenide. How to calculate lambda de Broglie? So, we know that lambda is equal to h by p, where p is the momentum, h is the Planck's constant. The thermal energy of electrons, electron has thermal energy E is of the order of kT. Corresponding to these electrons, thermal electrons, I want to find out what is the corresponding de Broglie wavelength. So, this is E is equal to T square by 2m, m star in the medium, or P is equal to square root of twice m star E, and lambda is equal to h by p. So, this is equal to h by square root of 2 m star E. I am calculating the average de Broglie wavelength of electrons in a semiconductor. And if I take gallium arsenide for example, then we know m star for the conduction band electrons is equal to 0.067 into m0. So, if I substitute in this expression here, h is equal to 6.6 into 10 to the power of minus 34 divided by square root of, so to the power half, 2 into m star 0.67 into m0, which is 9.1 into 10 to the power of minus 31 kg. M star is this much into m0 into E, kT is equal to 0.025 eV, but rest are all in SI units. So, you have to convert this into joules, 1.602 into 10 to the power of minus 19 whole to the power half. simplify this and you will see that this comes out to be approximately I think 297 angstroms or approximately 300 angstrom. I think 297, please check, use the calculator and check, approximately 300 angstrom. This is the de Broglie wavelength of electrons in a semiconductor in gallium arsenide. We have calculated for gallium arsenide. Therefore, if the dimension, if the thickness of the layer is less than 300 angstrom or of the order of 300 angstrom, we have a quantum well structure, a structure in which quantum size effects become important. So, quantum size effects refer to the effects which lead to discrete energies for electrons, discrete energies for electrons. Let me go a little bit further. Therefore, what is a quantum well structure? And how does a quantum well structure form? We have talked about double hetero structures where you had a substrate, on top of this you grow a layer. Let me put typical materials, say gallium arsenide, on which n gallium arsenide, n plus, I am taking a typical structure which is used in laser diode, for example, n plus gallium arsenide or aluminum gallium arsenide, Al 0.1, today's example Al 0.1, gallium 0.9 and arsenic. So, n plus aluminum gallium arsenide. On top of this we grow a thin layer. Let me put some typical numbers. If you take a substrate, then generally this is anywhere from 60 to 100 micron. So, let us say 60 micron. This is not to scale, and on top of this you grow a layer here, generally 1 to 2 micron. Okay. So, let us say 1 micron or 2 micron, 3 micron, that is the kind of numbers, 1 micron, this layer. And on top of this we grow a thin layer, let us say gallium arsenide, intrinsic or lightly doped P or lightly doped N, gallium arsenide. This layer thickness is generally, I am drawing the layer thicknesses of a double hetero structure, double hetero structure. Gallium arsenide, thickness of 0.2 micrometer. Some numbers will make it it will give you a good idea. So, this layer here intermediate is 0.2 micrometer. On top of this we grow another layer which is P plus or P, aluminum gallium arsenide, Al 0.1, gallium 0.9, arsenide 0.9. This is again let us say about 1 micron, okay, almost 1 micron thick. On top of this generally one grows a P plus layer of gallium arsenide, P plus gallium arsenide. Why do one need all these layers? This is a technological reasons and also physics involved, and on top of this you have the metal for contacts. At the bottom electrode, metal electrode. So, this is also metal, and top electrode here, top contact, and then we have a p plus layer. We will discuss this. This forms an ohmic contact. There are Schottky contacts and ohmic contacts. So, this forms an ohmic contact with the p plus and a metal or an n plus and a metal, and this is a double hetero structure, and there are two hetero junctions as we have already discussed. You can see here. So, this is p gallium arsenide, then there is a p-n junction here, there is a p-p junction here. So, there is one hetero junction here and one hetero junction here. Hetero junction is junction between two dissimilar semiconductors. So, we have two hetero junctions here, hence this is a double hetero structure. I have given typical numbers for the thickness of the layer. So, 0.2 micron is the thickness of this intermediate layer, which is the active layer, as we will see later. 0.2 micron is 200 nanometer or 2000 angstroms. This is a double hetero structure. If we reduce this dimension of the active layer, if we go on reducing, bring down to 200 angstroms or 100 angstrom, what results is a quantum well structure. It is a double hetero structure where the thickness of the active layer is very thin or very small. The thickness is very small. It is of the order of 100 angstroms. So, where is a quantum well structure? What is a quantum well structure? You can define it in different ways. Quantum well structure is a double hetero structure. It is a semiconductor double hetero structure where the thickness of the active layer is of the order of 100 angstrom, where the thickness is less than the de Broglie wavelength of electrons in the medium. So, quantum well structure is basically a double hetero structure, but the thickness has been reduced. If you see the now why quantum well structure, where is the well will be the next question. If you want to ask where is the well in this, let us see where is the well. So, the well here refers to the potential well. If you zoom this, what I am doing is I will rotate this through 90 degree and zoom only this region, zoom this region only. Aluminum gallium arsenide has a larger band gap compared to gallium arsenide. You remember that Eg of x was equal to 1.424 plus 1.247. I had truncated to 425 and 25 x, which means for x greater than 0, it is greater than that of gallium arsenide. This is that of the gallium arsenide. Therefore, these layers have higher band gap. So, two things I am doing. I am rotating this at 90 degree. So, I am showing the layers here. This is that gallium arsenide layer which was 0.2 micron and this is 1 micron. So, I have rotated this through 90 degree. So, 0.2 micron and 1 micron. I want to plot the band diagram of these. This is gallium arsenide and this is aluminum gallium arsenide, 0.1, 0.9 arsenide. What is the band gap corresponding to x equal to 0.1? So, we calculated this, it was 1.55. So, this is 1.55 eV, this is 1.42 eV, 1.55 eV. I plot the band diagram here corresponding to each of these media, the energy band diagram. So, I have this is Eg. So, this is Ec, Ev, and this is Eg of aluminum gallium arsenide, that is 1.55, and this is 1.4. So, this is gallium arsenide. So, this is 1.4, and this is again 1.55. What is this axis? Energy. There is a difference in band gap energy, and what we have here is, if you see this conduction band here, what we have is a finite potential well. The famous problem in quantum mechanics, particle in a potential box. This is V0. So, let us say x equal to 0 or z equal to 0. Particle in a potential box. If it is an infinite potential, then this goes continuously. Otherwise, this is a finite potential well. So, what you have here is a potential well, and this well is quantum well. This is the potential energy variation, potential energy well. So, that is the quantum well. When will this become a quantum well? This will become a quantum well when this structure is thin enough so that quantum size effects come into play. Right now, there are large number of allowed states here, because it is a bulk semiconductor. Here also you have very large number of allowed states. Here also you have very large number of allowed states. Allowed states for electrons. Electrons can occupy any of the states. Similarly, you have large number of allowed states for holes and large number of allowed states. This is a double hetero structure. This is not a quantum well. Right now, this is a double hetero structure. But if you reduce the dimension, then the number of allowed states decrease, and you reach a stage when you call that it is a quantum well. And when the dimension of the well becomes less than the de Broglie wavelength, then we have finite number of solutions. The allowed electron energy values are finite, and we have a situation where now this well dimension is very small. Let us say, for example, 100 angstrom. This potential well is now a quantum well, and in this we do not have so many allowed states. There are very few allowed states. So, we have energy levels E1, E2, E3, E4. Similarly, in the lower level allowed states for holes, so we have E1 dash, E2 dash, and so on. So, now with this picture, what is a potential quantum well? A quantum well structure is a double hetero structure where the intermediate layer, the active layer, the thickness of the active layer is of the order of 100 angstroms or 10 nanometers. Why the number has come? It is not 100 of the order, it could be 150, it could be 200, it could be 20 angstrom. This is a quantum well structure. Why did I bring it here? Because we saw that in the case of strained layer epitaxy, the kind of thickness of the layers which were required were of the order of 50 to 250 angstroms, and that indeed correspond to the thicknesses of quantum well structures. Hence the title strained layer epitaxy and quantum well structures. In fact, there are many devices which are called strained layer quantum well devices, strained layer quantum well devices, because strained layer epitaxy works out well without any defects only when the dimensions become very small. So, if you plot, for example, if you plot epsilon here versus the critical thickness dc. So, let us say epsilon 0.01, 0.1, okay, 0.0, let me take smaller values, that is 0.1%, 1% and 10%, 5% somewhere in between. Just I want to find a plot. So, what kind of numbers will we get? 50, 100, 150, 200, 250 angstroms. These are all in angstroms. I had calculated already for 1% and 10%. For 1% it was 25. For 1% it was 250 angstroms. I had taken example just now with the AS is equal to 5 angstrom. So, you saw this is DC, critical thickness was 250 angstrom here. For 1% 250 is it? Please check. 250 angstrom, and for 10% we had 25 angstrom. For 5% you will have 125 angstrom. Actually, I should have taken even smaller. You could also find out for 0.1%. So, this will go to 2500 angstrom, which means basically if you plot such a curve, this will come down rapidly, DC versus epsilon. Use a proper scale. The critical layer, the critical thickness of the layer, critical thickness of the layer drops rapidly with increasing strain, but the numbers involved are of the order of 100 angstroms, and strained layer epitaxy therefore always goes along with quantum well structures if you want to defect free layers. And what is a quantum well structure? It is basically a double hetero structure where the thickness of the active layer is of the order of 100 angstroms. We will talk a little bit more on this. These have very important advantages of strained layer epitaxy. In the meantime, let me recall little bit of quantum mechanics that we have studied and see how the energy varies, allowed electron energy varies with the well thickness. Recall your recap, your basic quantum mechanics of particle in a potential box. Okay. First, we have an infinite well. So, this is V equal to 0 and it's going to infinity. The first problem that so this is Z equal to 0 and Z equal to L. The solution of one dimensional solution, so d square psi by dz square plus 2m by h cross square into E into psi equal to 0. The one dimensional Schrodinger equation. The one dimensional Schrodinger equation. So, this I can write as d square psi by dz square plus, let me call this as k square. So, k square psi equal to 0, where k square is equal to 2m E by h cross square, or E is equal to h cross square by 2m into k square. H cross square k square by 2m, E is equal to the allowed energies. So, where k, these k's are given by q times pi by Lz L, where this is, we have already seen this, k is equal to q times pi by L, where L is the dimension of the structure. So, this gives energy values here. Please see that if you substitute this here, this is h cross square by 2m, h cross square by 2m into q square, or pi square by L square into q square. And what is q? Q is equal to 1, 2, 3 integers. So, if you put q is equal to 1, this is the first one, that is E1. So, E1 is here, and next will be 4 times q equal to 2. So, q square. So, you will have E2 here, this is E2 is equal to 4 times E1. And what kind of wave functions? If you solve this, what will you get? You will get solutions of the form psi is equal to a sin kappa z, a sin kz, a sin kz, and this is inside the well here, and outside inside the well. And outside field is equal to 0, because it is an infinite rigid wall. Rigid wall boundary condition means the field has to go to 0, the wave function has to go to 0 there, and therefore, the wave functions, if you see, they look like this is the first solution. Of course, this is the second solution. A very quick recap. So, these are the psi. So, this is psi 1 and this is sinusoidal. As you can see, it is sinusoidal, and k contains a q there, and therefore, you have various solutions. So, these values can be directly obtained. You see in this expression, if I give you a well of dimension 100 angstrom, all others are constants. H cross is constant, m is constant for the given material, only L. So, depending on dimension, we have different values of E. This is the basic problem of infinite potential well. What about finite potential well? So, if we next go to the problem of a finite potential well, same 0, same L, but now this is not infinite, but this height is V. Always the vertical axis is energy. So, this is now V. So, this is V equal to 0 and this is V is equal to V. what kind of solutions will we get? Same Schrodinger equation you have to solve, but there is a difference now that outside also there is a finite potential here V. Earlier we had only V equal to 0 and there is no field outside because of the rigid wall boundary condition. But now there is a finite value of V. So you have to write equation for the outer region, which is d square psi by dz square plus 2m by h cross square into E minus V into psi equal to 0. There is a V which has come, potential energy E minus V psi equal to 0. And what kind of solutions do we get? If you write the fields, I am not going to solve this, it is only a quick recap. Those of you who have not done, please see any of the basic quantum mechanics books. So you can write the fields. If I call this as 2m gamma square equal to 2m by h cross square into V minus E. If this term here with a negative sign, why negative sign? Because V is higher. We are looking for bound states. What are bound states? So we are looking for bound states. Bound states means the energy remains within this, it is bound to the well, which means you have oscillatory solutions inside and exponentially decaying solutions outside. They are the bound states, that is 0 less than E less than V are the bound states. Therefore, V is greater than E and therefore, I flip this and then you write the field solutions. You can write psi is equal to some constant A. This is just as a revision, e to the power of gamma z. This is B into sine some constant k x k z plus delta. You can write it in different form, plus delta, where delta is a constant, and c e to the power minus gamma z. This is for z less than 0, that is this side, this is z axis. Z less than 0, this is the solution for 0 less than z less than L, and this is the solution for z greater than L, which clearly tells you the solutions are exponentially decaying. So, if you see the solution here now, E1, so this corresponds to E1, you will get a field variation, a wave function variation, which is like this. It is finite. The continuity of field boundary conditions, so the continuity of psi and its derivative gives you a field which is of this form. The wave function has exponential tails outside in a finite potential well as compared to an infinite potential well where the wave function is 0 outside. The energy E1s are obtained if you apply the boundary conditions to this at every interface at z equal to 0 and z equal to L. If you apply continuity of field and its derivatives, continuity of wave function and its derivative, you get an eigenvalue equation which is tan kappa d kappa L, tan k L is equal to gamma by k. This is a transcendental equation. You have to solve this numerically to get the solutions. Solution means to get the value of E. This is called the eigenvalue equation, and the solutions will give you the energy eigenvalues, the E1, E2 here, and that will also give you the wave function psi. So, this is how we determine the energy in a potential well, a particle in a potential well, the standard problem that which we had in quantum mechanics. There is something interesting which I want to tell, but I think we will stop here and continue in the next class. and we will see how the energy depends on the dimensions of the well and how this is used for band gap tailoring or band gap engineering. So, this will be our next topic.